We've now looked at a couple of cases where we used the concept of relative displacements and relative velocities in order to obtain the time taken by two bodies to meet. And in both those cases, the velocities were uniform, so there was no relative acceleration. Now let's try to introduce acceleration into the movement of A and B and check if we can apply the equations of motion when there is relative acceleration between the two bodies. When we obtained the relative velocity of B with respect to A, it was simply the difference in their velocities as computed from the ground frame of reference. What about relative acceleration? Can we use the same formula? Let's differentiate the relative velocity equation with respect to time, and we obtain the relative acceleration of B with respect to A as AB minus AA. So the acceleration of B with respect to A is the acceleration of B with respect to the ground minus the acceleration of A with respect to the ground. And this very much resembles what we had as the relative displacement of B with respect to A and the relative velocity of B with respect to A. Let's begin by attaching the frame of reference to A. This is as witnessed by the observer from the ground frame of reference. But what we would like to do is to visualize this from the eyes of A, the observer. So we need to rewrite all the motion equations where the observer A is moving and not stationary on the ground. These are the three equations of motion. When we rewrite these from A's perspective, that is, assuming A is the observer, we write these equations exactly in the same form as we do when the observer is stationary. The only difference is that the displacements, the velocities, and the accelerations are expressed from A's perspective. So we see the subscripts as B with respect to A in red. To apply these, A assumes himself to be at rest, and that B has a displacement, has a velocity, and has an acceleration, and that is the basis of the computation. And just like the equations of motion from the ground frame of reference, these are valid when the relative acceleration of B with respect to A is constant. We have a red ball A and a blue ball B initially separated by 200 meters. A moves to the right with an initial velocity of 50 meters per second and an acceleration of 5 meters per second squared. B also moves to the right with an initial velocity of 25 meters per second and an acceleration of 2.5 meters per second squared. And they meet at point C, and we have to find out the time taken to meet at point C from the time they start off at their respective positions. This animation is from the ground frame of reference, so as seen by a person on the ground. Let's watch it from A's frame of reference and solve this problem directly using relative displacements, relative velocities, and relative accelerations in our approach. So from A's perspective, A pretends that he is at rest and he sees B approaching, but this time B is not approaching with a uniform velocity but is accelerating as well, since the acceleration of b with respect to a is non-zero. The initial relative displacement will be the distance AB, which is given to us as 200 meters, and the final displacement of b with respect to a will be 0, since they meet. The initial velocity of b with respect to a will be minus 25 meters per second, and the initial acceleration of b with respect to a will be minus 2.5 meters per second squared. And since the relative acceleration is constant, we can apply the equations of motion to b with respect to a. Let's plug these values into the second equation of motion. And these values have to be the values of the displacements, velocities, and accelerations of b with respect to a. We had the initial displacement as 200 meters, the final displacement as 0, the initial velocity as minus 25 meters per second, and the acceleration as minus 2.5 meters per second squared. So we obtain a quadratic equation in time t, which we have to solve for. Solving, we obtain the time as 6.12 seconds. So you can see that with this approach, the first step is to fix the frame of reference to A and assume that A is stationary. The second step is to obtain the measurements of displacements, velocities, and accelerations of B with respect to A, which is nothing but their differences from the ground frame of reference. And finally, to plug this into the equations of motion, and this will be valid provided the relative acceleration of B with respect to A is constant. We could apply the equations of motion to a moving object as seen by another moving object, but provided the relative acceleration between the objects is constant.